Hi, welcome to another session of Basic Electrical and Electronics Engineering. In today's class 5, under DC machines, we are going to see some numericals and their solutions on critical resistance and critical speed of DC shunt generator. So, in order to understand the characteristics of DC machines, especially DC generator, we need to know how the performance of DC generator is obtained by looking into its characteristics. So before understanding the characteristics, let us have a glance over the open circuit characteristics of DC shunt generator under no load. So in order to understand this concept in a better way, we have selected some numericals. So before that, what is critical speed? What is critical resistance? All the basics we are going to see. So we'll start off with this. First, what is a magnetization curve? Means what is meant by a saturation curve? If at all you want to give you the answer in electrical machines, the curve giving relation between flux per pole and field ampere turns per pole is known as magnetization curve. It is also known as saturation curve. So the next question would be how to obtain saturation curve of DC generator. For this, the answer is the EMF generated in a generator is given by E is equal to 5 P N Z by 60 into A, where P is the number of poles, N is the speed, Z is the number of the conductors. This 5 represents flux per pole and A represents parallel paths. This 60 is a constant. So for a given machine, for example, a machine is given to you and it is made to run at some kind of speed, then what happens? So in that case, for a given machine, the poles will be fixed. Means it could be a 2-pole machine, 4-pole machine, 6-pole machine, like that. The poles will be given and the parallel paths will be allotted. How many conductors are there? That conductors value can be given by the value of Z. 60 is already a constant. So whole this constant, I'm separating it with flux and speed such that E will be equivalent to K phi N. For a given machine, K represents here constants and thereby generated EMF in generator is directly proportional to product of flux per pole and speed. Fine. If the generator runs at constant speed, then EMF is directly proportional to flux per pole. From this equation, E will be proportional to phi. Since E is proportional to phi at constant speed and field ampere turns E is proportional to field current IF for shunt machine, therefore, if a curve is drawn between generated EMF at no load, means machine is not loaded, and field current at constant speed, then the curve so obtained will be similar to a saturation curve. Such curves are known as magnetic characteristics or open circuit characteristics. So that is also known as OCC. You have to note in this concept that the saturation curve for DC generator does not start from zero ordinarily, but at some value slightly higher than zero due to residual magnetism. What is this residual magnetism? Residual magnetism is a magnetization left behind in a ferromagnetic material such as iron after an external magnetic is removed from the circuit. So all these basic concepts you can go through in different textbooks or different literatures given by different authors. So especially when you look into electrical machines, that is theory of electrical machines by J.B. Gupta, you can find out these basic definitions. From that, how to draw this saturation curve? You see, the saturation curve is said to be obtained between E naught and IF. As we have already seen that E is proportional to flux and field current is proportional to field ampere turns, and magnetization curve is nothing but it is a graph between flux per pole and field ampere turns per pole. So here the field ampere terms is represented by IF because it is proportionality, and E naught it is replaced by flux per pole because of the derivation what you have seen in the last slide. Okay, when you are going to draw a graph, you're going to get an OCC or saturation graph like this. So this is called as OCC curve, and already it is given a note that uh, the curve is not going to start from zero but some with some value, means what, with zero field current some voltage is developed. That voltage is known as residual voltage, and this particular portion it is shown as the part due to residual magnetism. And practical conditions will ignore this, and shunt field resistance line is drawn from 0 and it is cutting the curve at A. So this point will be the value at which the machine will get completely excited through some voltage, and tangent line to this curve is drawn in order to obtain the critical speed. So we are going to see what is the critical speed and critical resistance. So critical load resistance is defined for DC generator in no load conditions, that if a line tangent to external characteristics and passing through the origin, neglecting the initial ordinate due to residual magnetism, the resistance represented by the slope of this line is known as critical resistance. So we have to remember in the condition that critical resistance is the maximum resistance with which generator will be able to excite. So this is what is critical load resistance, whereas critical field resistance is the maximum voltage which a generator can generate, is given by the point of intersection of the field resistance line with the open circuit characteristics, that is known as critical field resistance. And critical speed, you can obtain the critical speed of a shunt wound generator, is that speed for which uh, the given shunt field resistance will represent the critical field resistance. So we are going to understand this concept better way when you are drawing the graph for a particular given values of a machine. So how to draw this OCC curve, how to obtain the critical resistance, and how to obtain the critical speed. This is our point of interest. So to determine the critical speed, we need to draw the OCC graph, and we have to draw a line tangent to OCC graph, and also a line representing the shunt field resistance. Then draw any ordinate intersecting the field resistance line and tangent line to given OCC. Then multiply the given speed by the ratio of the intercepts of the ordinate drawn between field resistance line and abscissa, and between tangent line to the given OCC and abscissa. So all this information you can easily obtain from Theory and Performance of Electrical Machines by J.P. Gupta. It's a very good author. You can go into different numericals, or complete basics are given by Theory and Performance of Electrical Machines by J.P. Gupta. Also, you can follow Electrical Machines by P.S. Bimra. That is also a good book. So for machines, these two books are good, and for numericals, you can go on with Electrical Technology by B.L. Thareja. That is also a good book. So already we have seen how to draw an OCC curve. Now slope of this tangent, that is given by this PQR triangle. So PR represents the parallel combination of Y axis, which is given by E naught, and QR it is parallel to X axis, which is nothing but I, and PR if represented by voltage and QR represented by IF, then voltage by current will give you the resistance. So that resistance here we're treating as critical resistance, that is PR by QR, that gives the value of critical resistance per given machine. And if at all I draw this particular ordinate, which is perpendicular to the tangent line, perpendicular to shunt field resistance line, and I'm marking the points as M and K, nothing but NK divided by MK and multiplied by the given speed will give you the value of critical speed. In order to understand in a better way, let us go with the problem. So in the first problem, the magnetization curve of a DC generator at 1500 RPM is given by the following table. So you can see IF in amperes and E naught, that is the armature voltage, they are tabulated here. So for 0 it is 5.8. This is because of residual magnetism, and current is increased from 0 to zero point 0.2, then 0 0.4, 0 0.6, 0.8, and so on. It goes till 3. Corresponding to this current, the voltage it is obtained as 5.8, 32, 60, 90 respectively, and goes to 242. So what we need to find? For this generator, we need to find no load EMF for a total shunt field resistance of 114 ohms, critical field resistance at 1500 rpm, and critical speed. So this is the data which is given, and what is we need to find out the parameters, that is nothing but critical resistance, critical speed, and no load EMF. So from electrical technology by BL Tareja, you can find these kind of problems. So here you can see I have drawn a graph. I have represented the values on x-axis and y-axis based upon the tabular column given. So here E naught is there, here IF is there with y-axis and x-axis respectively, and we need to plot for 0 it is 5.8, so 20 is over here, so this would be 10, this point would be 10, and 5.8 will be approximately this line above. So roughly you can see I have drawn for 0 5.8 over here. So point 2, for point 2 it is 32, so this particular line roughly we have taken the value as 30. For point 4 it is 60. For point 6 it is 90. For point 6 you can see it is 90, and for point 8 it is 122. So point 8, so here it have 120, above this will be 125. So between 125 and 120 roughly we have taken the value as 122. Then for 1.2 it is 174. You can see 160, 180 is here, so in between 160 and 180 it will be 170, and above 170 and below 180 you have 175. So roughly I have taken here 174 approximated to 175 value here. You can draw on a normal graph with particular values. You can easily plot the exact values like 174 or 204 or 222. Correspondingly, for various values of current, the voltage is plotted like this. So all these dotted lines you can easily cover with a graph which is drawn pointing out all these points, and particularly it is obtained as OCC graph. So this is how you need to draw the saturation curve or no load curve for given tabular values. Fine. Our intention is to find out the critical speed, critical resistance, and the voltage to which the voltage, that is no load voltage, which has reached with the help of the resistance. So what is the resistance value given? The resistance value is given as 114. So for point 1, 114 would be over here. So you can see this is 114 we need to obtain. So 114 can be obtained approximately as voltage is 114 divided by current 1. Voltage by current, that is 114 divided by 1 is nothing but 114 ohms. So with this I have drawn the shunt field resistance line, and this is cutting approximately at point A, and that point here is the value of no load voltage which is going to get excited at 220 volts. So this is our first intention, that is no load voltage to which it is getting excited, that is 220 volts. Now a tangent is drawn to this OCC curve, and slope is identified with the points P, R, and Q like this. So you can easily take the values here. For R, you can see the x-axis value is approximately 1.45 because it is 1.4 over here, 1.6 over here. So naturally this will be 1.5, and this line will be 1.45. So 1.45 is selected here. So the same point here P, you have the x value as 1.45, but the values of y are changed. Here you can see the value of y is 140, whereas at P the value of y is approximately 225. In this particular point it is 225. Fine. So the P and R values are selected like this. Similarly, you can select the value of Q. Q at this particular point, it is between 0.8 and 1. So this middle value will be 0.9. Whereas Y value remains the same because of this ordinate representation. The Y value is 140. So now you can easily get the value of slope of this particular triangle. So critical resistance is nothing but the difference of the voltage by difference of the current. So you can see the Y values are taken on numerator and X values are taken on the denominator. So 225 minus 140 will give you the value of voltage, and 1.45 minus 0.92 approximately will give you the value as 160.377 ohms. So when you're going to draw on a particular graph, you can get more approximate value. So here we got the value of critical resistance as 160.377 ohms. All of you please try to draw this on a normal graph and check the result and comment on the chat box whether you are getting the same answer or not. I hope you are going to get answer of critical resistance which is nearer to this value. Now I'm going to do I'm going to take a perpendicular line which is cutting the tangent line as well as the shunt field resistance line. So your tangent line and shunt field resistance line are cut at M and N and K over the x-axis. So with this, I'm going to get the critical speed value as Nk by Mk into 1500. 1500 is the value of the speed which is given. So you can see here Nk, N and K, approximately it is 144. Mk, it is approximately 195. So 144 by 195 into 1500 will give you the value as 1107.69 rpm. Again, this value you have to cross check by drawing the graph on a normal graph sheet of OCC and determine the value of critical speed. Approximately, you are going to get the nearer value to 1107.69 rpm. So this is how we solve the critical resistance and critical speed for a given values under tabular column for a DC machine. So for this machine, the solution here is nothing but no load EMF for a total shunt field resistance of 114 ohms is 220 volts, what we have seen. Critical resistance is obtained as 160.377 ohms and critical speed is 1107.69 rpm. Let us go with another example. The following table give the OCC of a DC shunt generated at 600 rpm. The IF and E0 are given. Plot OCC for 720 rpm and determine the voltage to which the machine will excite if the field circuit resistance is 30 ohms. Okay. What additional resistance would have to be inserted in the field circuit to reduce the voltage to 232 volts at 720 rpm? Okay, the machine voltage is being reduced to 232. Okay. Without this additional resistance, determine the load current supplied by the generator when its terminal voltage is 232 volts. Okay, we need to find out additional resistance. We need to find out the total load current without the additional resistance, and given the armature resistance value is 0.2 ohms. So clearly you can see the machine is made to run for 720 rpm. For example, 600 rpm, you have this particular tabular values of field current and armature voltage. We need to determine first the OCC and the value of voltage to which the machine will be excited when the machine is made to run at 720 rpm. Okay, when 720 rpm the machine is made to run, and we need to find out the additional resistance that would be required for the field current to reduce the voltage to 232 volts at 720 rpm. Fine. Now what we have to do, first we'll take this new rpm, that is 720 rpm. It would be increased in the ratio 720 by 600. So the new value of speed is 720, old value of speed is 600. So corresponding to the different shunt field currents, that is IF value which is given in this particular numerator, we need to find out new voltage values by multiplying by the ratio 720 by 600. So we have to take 720 by 600. Approximately the value will be 720 divided by 600. The value is 1.2. So multiply 1.2 with 0.8. I'm going to get 600. 1.2 you have to multiply with 8. So we are going to get 9.6. So correct this value. For 0, the new value of voltage is 9.6. For 2, field current, multiply 1.2 with 95. So 1.2 multiplied with 95, you're going to get value as 114. Similarly, for a field current 3 amperes, multiply 136 with 1.2, you're going to get 163.2 volts. Likewise, you carry on the calculations and exactly at 8 amperes with the 206 as old value of voltage for 600 rpm, I'm going to get 206 multiplied with 1.2, I'm going to get 247.2 volts. So this is the new table we have created with the machine assumed to be running at 620 rpm, sorry 720 rpm. So with this tabular column and the graph, we need to plot the OCC as well as the shunt field resistance line. So OCC is drawn like this, and 30 ohms it is given. So approximately for 30 ohms, here 30 you can see 20 is there, above that you have 30, beneath of this 40, the center line. So for 30 ohms, this is the shunt field resistance line, this is down here, and the machine will be excited at approximately 246 volts, that is at 8 amperes the value is 246 volts. So this is the saturation voltage. Now at 232 volts, the speed is increased and the voltage value is reduced. For example, the voltage value is reduced to 232 volts. For 232 volts, what will be the field current value? 5.5 amperes. So 232 by 5.5 amps, I'm going to get the value of field resistance. I'm marking as RF1 because already the shunt field resistance line is 30 is given. That is down here. So this RF1 value is the new value of the resistance of the field when 230 volts is reduced, corresponding to 5.5 amperes. I'm going to get 42.18 ohms. So this is the value of change in value of resistance for 232 volts. Now the magnetization plot is drawn in the graph, and shunt field resistance of 30 ohms it is also taken consideration, and from the graph the voltage to which the generator will excite is estimated to be 246 volts, represented by OG, what we are seeing in the graph. In this graph you can see 246 volts. So O and G represents the excited voltage line. It can be observed that for exciting the generator to 232 volts, the current is 5.5 amperes. So the value of field resistance is 42.18 ohms. Therefore, the additional resistance required it is asked. So the additional resistance would be, the old resistance is 30, the new resistance is 42.18. So 42.18 minus 30 will give you the value as 12.18 ohms. Without this additional resistance, we need to determine the load current supplied by the generator when its terminal voltage is 232 volts. So without this additional resistance, the given value of voltage is 232, unchanged value of resistance is 30. So that value will be 7.73 amperes. So for 7.73 amperes, the exciting current for this value, the voltage would be 244 volts. So roughly for the value of 7.7, approximately here, the value will be, see, you have 240 here, 246 here, so naturally between 240 and 246 the rough value is 244. That is what it is shown here, 244 volts. So for the generator we have E is equal to V plus IARA, therefore IARA will be equal to E minus V. So the RA value it is given as 0.2. So with that I'm going to get the value of armature current, which is nothing but 12 divided by 0.2, which is 60 amperes. We need to find out the load current. So the load current value will be obtained because of the shunt conditions. IA is equal to IL plus ISH. So IL will be equal to 60 minus 7.73. Knowing the shunt field resistance, shunt field current, I'm going to get the load current value as 52.27 amperes. So these type of problems are frequently asked in the exams. I hope you understood how we have obtained the load current for different values of resistors. Okay. And another problem, the machine is running at 400 rpm. We need to obtain the critical speed, critical resistance for 34 ohms. Okay, we need to find out the voltage to which the machine will excite when machine runs as shunt generator at 400 rpm. The field resistance is 34 ohms. And then we need to find out the resistance of shunt circuit to reduce the open circuit voltage to 220 volts. Again, the resistance value is changed, and that resistance value we need to find out for 220 volts. Also, we need to find out the critical value of the shunt field resistance, and finally the critical speed when the field circuit resistance is 34 ohms. Okay, so with these values of the tabular column, I'm going to get the OCC graph like this. Shunt field resistance line for 34 ohms, it is like this. So you can see 34 is roughly taken over here. This is 20, this is 40. So between 20 and 40 the value will be 30, and above 30 you have 35, and after that you have 40. So below 35 I have taken the value as 34. So this is how the shunt field resistance line is drawn. Point A is marked over here, and tangent line is also drawn to the OCC. Then exactly at 7.37 amperes we are going to get the value of no load voltage, that is saturation voltage, as 250 volts represented by OG. And again tangent is drawn like this. Critical resistance is obtained by difference of the voltage by difference of the current, which is 53.57 ohms. And the machine is reduced to voltage to 20 volts. So 220 volts, the current would be 5.42 amperes. So the change value of resistance, that is shunt resistance, would be 220 divided by 5.42, that is by 40.6 ohms. So this is the value of resistance per reduced voltage 220 volts. Then again a perpendicular line is drawn on tangent as well as on shunt field resistance line, mark the point as M and K, and critical speed can be obtained by 126 divided by 200 multiplied with the speed 400. So the value would be 252 rpm. So with these numericals you have understood what is critical resistance and critical speed. You can do different problems, or you can solve unsolved numericals by taking any reference textbooks like J.P. Gupta or P.S. Bimra or Critical Technology by Tereja and Tereja, and solve different problems on critical speed and critical resistance, and comment in the chat box whether you are able to find the values or not. In the next class we are going to see the characteristics of different types of DC generator. Uh, Once we have understood what is this no load voltage, no load characteristics, magnetization characteristics or magnetization curve, with this basic problems we will be able to understand how the characteristics of DC generators are used to understand the performance of the machine. So in this problem we have seen that the voltage to which the generator will excite is 250 volts, and in order to find the value of resistance of shunt circuit to reduce the open circuit voltage to 220 volts, a horizontal line is drawn from H towards OCC, which cuts it at point B, and that point corresponding to 5.42 amperes. We got the value of shunt resistance as 40.6 ohms. A line OC tangent to OCC is drawn to obtain the critical resistance, which is 53.57 ohms. And when you draw a perpendicular line which cuts the tangent line at M, shunt field resistance line at N, and touches the x-axis at K, then critical speed is calculated as 252 rpm. So I hope you have understood how we have solved uh, the problem of critical resistance and critical speed from the given data on the top left column. I hope you like this video. Please share and subscribe to this channel, and please press the bell icon for future notifications. Thank you.